This is a CIE IGCSE Physics Paper 6 Alternative to Practical talk through from October-November 2020. So question 1, a student determines the density of modelling clay by two methods. Figure 1.1 shows one face of a piece of modelling clay that the student uses. This is sample A. The student measures the depth D of sample A and finds it to be 3.2 centimetres. Measure and record the length L and the width W of the sample. Figure 1.1 is drawn to actual size, which means you can take your ruler, measure L, and you should find that value is 3.1 centimetres. Measure length W, and that should be 2.7. Calculate the volume VA of sample A using this equation. So just rewrite that. Substitute in your values, and your value is 26.8. Figure 1.2 shows sample A on a balance. Record the mass of the sample to the nearest gram. So to the nearest gram, we're looking for two significant figures, so we round up, so it becomes 51. Calculate the density of sample A using this equation. Give your answer to a suitable number of significant figures for this method and include the unit. So we do 51 divided by 26.8. Now in terms of finding the unit, just substitute in the unit of the mass, so that was in grams. The unit of the volume was in centimetres cubed. So you can see, once you've done your calculation, put that into your calculator. Let's do to two significant figures, just because we have two significant figures here, which is really the maximum precision we can go for. So our unit becomes grams per centimetres cubed. The student records the volume V1 of water in a measuring cylinder and finds it to be 150 centimetres cubed. He carefully lowers sample B of the same modelling clay into the measuring cylinder until it's completely covered with water. He records the new reading V2 of the water level in the measuring cylinder. Calculate the volume VB of the sample using this equation. So again, more substitution. V2 was 182, V1 was 150. Either do that in your head or using your calculator and you'll get a value of 32. The student measures the mass MB of the sample B and finds it to be 60 grams. Calculate the density of sample B using this equation. Give your answer to a suitable number of significant figures, include the unit. So MB was 60 grams. VB was 32 centimetres cubed. So your answer here is 1.9 to two significant figures, same units as before. A student suggests that the density of modelling clay is not affected by the mass or volume of the sample used. State whether your results agree with this suggestion and justify your answer with reference to your results. So let's have a look at these two values. For the density, we got 1.9 here, 1.9 there. They're the same number, so no, it's not affected by the mass or the volume of the sample used. So my results disagree with the suggestion. And why is that? Because both calculated densities are the same. Tick the boxes that describe the correct line of sight for taking a reading of the volume of water. Figure 1.3 shows the curved surface of water known as the meniscus. Okay, so where should your eye be? Well, it should be at right angles to the scale, which means that's the right answer. And in terms of how you read, remember you want the bottom of the meniscus always to give you the accurate result. Those are the answers here. 2. A student investigates the cooling of water under different conditions. Figure 2.1 shows the apparatus she uses. The thermometer in figure 2.2 shows the room temperature at the beginning of the experiment. Record this value. So read that extremely carefully and you should find that it's 21 degrees Celsius. Include a unit. The student pours 200 centimetres cubed of hot water into the beaker. She records the temperature of the hot water at time t equals 0. She immediately starts the stop clock. After 180 seconds, she measures the temperature shown on the thermometer and her readings are shown. complete the time column and column headings. So first of all, let's pick some units. Time is measured in seconds, temperature is measured in degrees Celsius. We know we started at t equals 0 and that we ran the experiment to t equals 180 seconds. Calculate the drop in temperature between time 0 and 180 seconds. So we're looking for the difference in these two numbers. That's 16 degrees. Calculate the average rate of cooling using this equation, where change in time is 180 seconds, include your unit. So we know our change in temperature was 16. Our change in time was 180 seconds. So our value here is 0.09 degrees Celsius per second. The student empties the beaker. She pours 150 centimetres cubed of hot water into the beaker. She adds 50 centimetres cubed of cold water. She repeats the timing and temperature recording procedure described in B. Complete the time column and column headings, so same as before. Time in seconds, change in temperature in degrees Celsius, 0 and 180. Calculate the drop in temperature. So we do 69 minus 57 to get a value of 12 degrees Celsius. Calculate the average rate of cooling R2 using that same equation. And again, we're being asked to find that unit. So change in temperature was 12 degrees Celsius. Change in time, 180 seconds. Put that into your calculator to get a rate of cooling of 0.07 degrees Celsius per second. A student suggests that the average rate of cooling R of the water depends on the difference D between the temperature of the water at time 0 and room temperature. Calculate the difference D1 using the readings in table 2.1 in your answer to A. We know that from A we can see that the room temperature is 21 degrees and we know that the starting temperature is 85. So we work out the difference between those two numbers to find D1. Calculate the difference D2 using the readings from table 2.2 in your answer to A. So we know that answer to A remains 21 degrees. What about 2.2? Well, this time we started at 69. So our answer here is 48. Write your conclusion about the relationship between R and D. Justify your answer with reference to your results. So we can see here that there was a much larger difference in starting temperatures for D1 compared with D2. Let's now look at the rate of cooling. It was 0.09 degrees per second versus 0.07. So we can therefore say that the greater the temperature difference, the faster the rate of cooling. As seen if you compare the rate of cooling of R1 with R2. Explain why the thermometer scale should be read at right angles. Reading perpendicularly or at right angles is all about avoiding parallax errors. Explain why the mixture of hot and cold water should be stirred before taking the temperature reading at the start of the experiment. That's to ensure that you have an even temperature reading. A student investigates the magnification of the image produced by a lens. Figure 3.1 shows the apparatus used. Figure 3.2 shows a triangular hole in a card that forms the illuminated object. Figure 3.2 is drawn to actual size. On figure 3.2, measure and record the height. Measure the length of this line here, and it's 1.5 centimetres. Always include units. The student places the lens at a distance U, 20 centimetres from the illuminated object. He moves the screen slowly until a clearly focused image is formed on the screen. He measures the distance V between the centre of the lens and the screen. He repeats the procedure using U values of 25, 30, 35 and 40 centimetres. Here are your readings. Calculate and record in table 3.1 the magnification for each value of u. Use this equation. So they've told us we're doing v over u, so we do this number divided by this number in every single case. Next up, 41.5 divided by 25, and just keep going. Plot a graph of u with centimetre units on the y-axis against m on the x-axis. Show your y-axis starting at u is 20 centimetres. So remember, that means we do a squiggle to show that we've compressed that scale. Then we draw our y-axis, label y. Let's draw our x-axis. We know that y is u given in centimetres. M doesn't have a unit, it's magnification. And we've been told to start at 20. Let's have a look. We go from 20 to 40. So we'll go up like this. Remember, you want to occupy as much of the scale as possible. What about for M? Well, we go from 0.64 all the way up to 3.55. I'm going to go up in 0.5s. Just practice. If you're not very happy with drawing graphs, honestly, practice, and obviously check the mark schemes. Now we're ready to plot. So we're plotting these numbers against each other. So 20 and 3.55, 25 and 1.66, 30, 1.08, 35 and 0.8, 40 and 0.64. Okay, now draw that line of best fit. I'm going to struggle on the iPad to go through the points. Okay, please draw it a lot smoother than that, but honestly I know my own drawing skills, that's as close as I'm going to get. Use your graph to determine the value of the object, distance u1 when the magnification is 1.0. Show clearly on the graph how you obtain the necessary information. That means you have to draw a line on the graph where m is 1 and show how you're reading across to the y-axis to get that u reading, which I think is 31. Calculate the focal length using this equation. So u1 was 31. We divide it by 2 to get a value of 15.5. Remember, everyone draws their graphs slightly differently, so there is some range here in terms of the answers they'll accept. State 2 precautions that you would take with this experiment in order to obtain accurate readings. So pick anything sensible here, such as using a dark room and a bright object. Move your screen slowly to find the best image. Ensure that the object, lens and screen are vertical. Use a clamp stand in order to hold the ruler in position. A student investigates the resistances of different wires. Plan an experiment to investigate the resistances of wires made from different metals. Resistance is calculated using this equation. The following apparatus is available. You can also use other apparatus and materials that are usually available in a school laboratory. In your plan, you should write a list of suitable metals for the wires you will investigate. Draw a diagram of a suitable electrical circuit using standard electrical symbols. Explain briefly how to carry out the investigation. State the key variables that need to be kept constant. And then draw a results table. Okay, so this is actually a really nice question. So let's work out our variables first of all. So our independent variable is what we're changing. We're using different metals. And remember, they want a list of suitable metals. So e.g. copper, iron, nickel, zinc, magnesium, anything sensible. What's our dependent variable going to be? What are we measuring? Now this is slightly more difficult because we're trying to effectively measure the resistance, but it's very hard to measure that directly from a circuit. Handily, they've told you what you need. You need to have the voltage value and the current value, which guess what? You can find the current using the ammeter and the voltage or potential difference using the voltmeter. So we're going to measure potential difference and current in order to find out resistance. And then what about our control variables? So what are we keeping the same? Length of wire, diameter of wire. These are both really sensible control variables. So I'm thinking I've done that. I've talked about this. We also need to draw a suitable electrical circuit using standard electrical symbols. So let's do that here. So here's your wire to be tested. I already said we need to be able to measure the current, which we do using an ammeter. Remember, that needs adding in series. We also need a power source, so I'm just going to draw a cell for that. And I also said we want to measure potential difference using a voltmeter. That needs adding in parallel to the wire. So something like this would be suitable. And as far as I'm concerned, that is adequate. This is the wire. Your independent variable, this will help list your simple method that they've asked for, is the metal type that the wire is made from. E.g. nickel, copper, iron, zinc, magnesium. Next up, your dependent variable is the potential difference measured using a voltmeter and current measured using an ammeter. I will substitute these values into the equation. Resistance is potential difference divided by current to find resistance, which is after all what the investigation calls for. What about our control variables? So what are we keeping the same? They include the length and diameter of the wire. And as always, we want to repeat and calculate an average in order to discount anomalies. How about this results table? We'll pick something sensible here. We need the metal type. We need potential difference with a unit, which remember is volts. We need current. The unit for this is amps. And we need resistance. The unit here is ohms. Let's draw the table outline. So if we have zinc, we have magnesium, we have iron and copper, nickel. So just to reiterate what we're doing, we'll find the potential difference using this voltmeter, which has been added in parallel. We'll find the current using this ammeter added in series. Then we'll use this equation here to find out the resistance, which we can then input into this column. So I'm actually really pleased with that results table. Then always check back. Have you provided suitable metals? Yes. Have I provided a diagram using standard electrical symbols? Yes. Have I briefly explained how to carry out the investigation? Yes. Have I said what variables I'm keeping the same? And have I drawn my results table? So I'm hoping, therefore, and I know I have got 7 whole marks, and that really didn't take too long.